Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience.
Hello everyone. Today we have with us Vivian Tong, who is a higher research scientist at the National Physical Laboratory near London in the UK. Hi Vivian, how are you doing?
I'm all right, thank you. Good to speak to you.
Wonderful. Let's start with understanding your career, scientific career so far. So, how did you end up in your current research field?
So I wanted to be a scientist when I was 6 years old. I don't know how much I knew about scientists, but I knew they invented stuff. And I read about Edison inventing the light bulb, and I thought that was really cool. And they find out how stuff works. And yeah, and originally I was more interested in physics. I guess it's a subject you do in school. But when I was applying to uni, I found out about this field or this course that you could do called material science, where you didn't just do physics, but you made it useful for engineers to build stuff with. So material scientists, I guess, design and develop materials that are better so that engineers can build better structures. So that's what my degree's in, and my and I am at the end I ended up doing a PhD where the research topic was on electron backscatter diffraction. And using it to study zirconium alloys, which is a metal that's used in nuclear reactors. And I thought about academic research, but then I found out also that you could do fundamental research, a mixture of fundamental and industrially relevant research in a non-academic setting. And now I work at NPL, or the National Physical Laboratory, where I develop new methods to interpret microscopy data, so that not just we get some useful, not that we don't just get some microscopy data, but we can also tell more and more useful things about the material we're looking at.
Okay, all right. That's really cool. That's amazing. That's quite an interesting journey you've had, and I liked your description of material scientists because I myself am a material scientist. That material science makes physics useful for engineers. So we are kind of this bridge between the basic sciences, so to say, and the applied sciences in a bigger scale. I really like the description. I think I'm
and
going to
not
use
just
that.
and not just physics, but also chemistry and sometimes
Absolutely.
biology.
Absolutely, yeah. With you, completely with you on that. I'm definitely going to use that later because most of my scientific career life, I got this remark that yeah, you're a material scientist, but you're more of a physicist, and then the chemist will be like, you're more of a the physicist would be like, no, you're more of a chemist, and then both the physicist and chemist would say that, actually, you're more of an engineer. So I really like your definition. How can you explain to us how and where does your current research fall in this big puzzle or this big picture of material science or materials or nanoscience at the moment?
So I work with engineering materials, so mostly metals, but some semiconductors to make that you make stuff out of. So say planes or bridges or nuclear reactors or computer chips. These are made of materials that have to be strong and last and perform a certain function and last as long as you need it to. And my research in microscopy, I look at both the microscale and nanoscale structures of these materials. And if we can understand them, we can then manipulate them and change them to make it better for the engineers to use later on.
Okay. So that sounds that's really interesting, and as you also mentioned in the previous podcast, you characterize all different kinds of materials from airplane material to drills to nuclear plants, computers. So it sounds to me like you do a lot of interesting experiments, or a lot of you are involved in a lot of interesting research projects. So if you have to pick one that you're most proud of, or the most quirky or the fun one, could you pick one and explain it to us in simple words in the section we call In Other Words?
Sure. So one of the projects that I had to do, I did in my PhD was on how these how these grains in so it was something that happens in well one of the things that I did in my PhD was look at the how one of some structures, some special structures formed in zirconium, which is the metal I was working on, which is used in nuclear reactors. So on the micro scale, zirconium is made out of any zirconium metal will be made out of crystals, small crystals packed together, and we call these grains. And usually they're about 10 microns in diameter, which means you could probably fit 25 of them into the width of your a human hair. But sometimes and for sometimes for some reason one of these grains starts eating all the grains around it, and it grows really big, sometimes to even a millimeter, half a millimeter or a millimeter in size. And the thing you need to know about zirconium is that it's used in nuclear reactors, and its shape in the nuclear reactors are these like 4 meter long thin walled tubes, and the tube wall thickness is only half a millimeter. So if you've suddenly got this big grain that's basically the entire wall thickness of this tube, that becomes a massive weak spot in the reactor, and you don't want that to happen. So the project I did was to look at, well, how do these big grains form? And then once we find out that how these big grains form, we can then look at, okay, what is the manufacturing routes used to produce these long tubes, or what are the temperatures and stresses and pressures in the reactor in operation, and how therefore can we make sure that these big grains don't happen and aren't found in nuclear reactors that we use in operation. The project was actually an accident. I was trying to do something else, but found that these big grains happen. Then I realized they were a big industrial problem, which was how I started working on it.
Wow, that's really fascinating. Wow, we hope to read more about it on while you're curating the Twitter account, and I hope there are a lot of pictures as well. And yeah, this is amazing. I can imagine why you picked this as the most proud of the project or research project for you. This is wonderful. Vivian, I hope yeah. Let's move towards more of the research experience now, and I hope that your research experience so far has been wonderful, and will continue to be amazing in the future as well. Having said that, if you had three wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
Okay. I guess, well, if you can't promise anything, but one of the things that noticed, actually, I didn't notice until I stopped working in an academic environment, was that access to journal publications is actually really expensive. And in most non-university settings, you click on a paper that looks interesting, you can see the abstract, and then you hit a paywall. So what I would love is, and there are lots of initiatives starting now, and have been probably been a while, is like to have more open access routes to access journal papers, and such as say preprints and the archive, where you can put preprints or postprints of papers, because frankly it makes sense. Um, uh, for for scientists to be able to benefit from other scientists' work that probably the same government or same group of governments are funding the research for. The second one is I would like to see a lower. I would wish for a lower barrier to entry for applying for stuff like research fellowships or research grants. Not so much in that I think it should be less competitive, but in terms of if you've had any experience with this, you'll know that you do 100, maybe 300 hours of work for an construct an application of something that has a success rate of probably 10%. And that doesn't make sense to me, because not just because it's a lot of work for something that may never happen, but also that a lot of this documents you have to put in aren't actually to do with the work itself, but kind of, I don't know, housekeeping or governance things that you have to put in, that actually could be asked for at a later stage when you've been shortlisted. So that would be what I would wish for, so that we can get more applications from people who maybe don't just have all the time on their hands, maybe have other caring responsibilities, or don't have cooperative brains, that kind of thing. The third thing I would wish for is an increased visibility of, I guess, non-academic research roles when you're in university. When I speak from personal experience, when you graduate from a PhD, then you see that this kind of linear career progression from I guess PhD student to postdoc to maybe research fellow to lecturer, and you can see all that and how that chain forms. But then if someone goes and works somewhere else, they say, oh, they went to work for this company, or they went into industry, and that's quite vague, and I don't know what that looks like. So I guess increased visibility of that kind of thing would be really great too, for lots of people who are just at the beginning of their research careers.
Yeah, that makes sense. I think all three of your wishes are quite. I can understand them completely, and I wish I could just grant it with just by snapping my fingers. But I hope that we are working towards achieving all three things, all three important things that you mentioned. And I hope we are working towards it. And I think talking about a researcher, at least for the third one, then talking about or showing or bringing forward the researchers like you who are not in academia per se. I think this is a good start as well, so that people know that there is research happening. Also, not there is a lot of research happening in university, but also in non-university places, there are also research institutions where research is taking place. I hope all three wishes, as I said, I completely understand them. Continuing the threes, and a bit about the future, what are you most looking forward to in the next 3 months?
So what I'm most looking forward to in the next 3 months is being able to go into work again, because at the moment, Right now it's the year 2020, and the coronavirus pandemic is spreading throughout Europe, and I guess like most people in, well, like many people in non-critical frontline roles, I'm working from home, and I don't have a microscope at home that I can do experiments from. So I can't wait, absolutely can't wait to go back into the lab and get on the microscope and do more experiments. But on the other hand, this I guess this being forced away from the lab and having to work from home has opened up lots of opportunities, and where I'm getting to do some new things at work, and um, focus a little bit more on the computational side of my research. So I guess I'm looking forward to being able to learning new skills now and being able to apply them in hopefully 3 months' time when I can get back in the lab.
Mm-hmm. Yeah, that's a positive way of looking at it. All the other opportunities that have opened up because of the lockdown. That's wonderful. And I hope that this pandemic is over or under control soon, and every one of us can go back to their jobs. Researchers, particularly, can go back into their labs. That would be wonderful. I can only imagine how difficult it is to not have an electron microscope at home that you can analyze with. I can
But at the
understand.
moment, it's more important to stay at home.
Yeah, absolutely, absolutely. You're right,
Yeah.
absolutely right. Um, we are strong. We can wait to go back into the lab because it's safer to stay at home and stay healthy at home. Vivian, before we let you go, what we want to understand from you is what are the challenges faced by your field of materials or nanoscience that the scientists are working towards solving, or the questions, the big questions that we are looking answers for?
So at the moment, my field, which is electron microscopy or electron backscatter diffraction microscopy, is very famous for producing very colorful pictures. It's also notorious for just producing colorful, pretty pictures that don't tell you a huge amount of new information about the material. One of the biggest challenges, or I guess questions, that I guess is limiting the field, is how can we interpret this really rich data to give us more information that tells us something useful about the material, as opposed to just a very pretty picture. That's something I'd love to work on more, that I have been working on as well, and I hope will be addressed, I guess, yeah, as we can get more data faster, that we don't just have terabytes of data that we don't use to the full.
Hmm. Hopefully, maybe the lockdown situation that the most of the world is facing right now, maybe this is the new big step that we will achieve as to not have this terabytes of data and actually making sense of it, more sense of it. Um, yeah, I can completely understand that. So, thank you very much, Vivian, for speaking with us. It was really nice to talk to you, and I learned a lot. So, thank you very much, and we are excited to have you on Real Scientist Nano.
Thank you. It was great to talk to you too.
Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.